Every single Bitcoin transaction ever made can be traced forever. Literally, forever. It creates a flawless public record. Meanwhile, one tiny mistake in our everyday banking system can, lock away your money, freeze an account, or just block a crucial transfer indefinitely. Most of us use digital wallets every single day without really understanding the invisible systems that are kind of failing us, or, more importantly, the revolutionary tech being built to replace them. In this explainer, we're going to dive into the fascinating mechanics of a blockchain block, see exactly how it works step by step, and uncover why it's fundamentally revolutionizing way more than just digital money. Let's get into it.
But to really understand the solution, we've got to look at the problem first. Picture this: 4 friends, Jack, Ted, Sam, and Phil, meet up for dinner. Jack generously covers the whole bill, and they all agree to split the expense later. The next day, Phil pulls out his phone, taps a money transfer app, and sends his share to Jack. Boom! It goes through without a hitch. Perfect, right? But then Ted and Sam try to send their respective shares, and suddenly, error. They get hit with messages citing issues at the bank. So why does a totally basic task, just 4 friends splitting a dinner bill, suddenly completely fall apart in the traditional banking system?
Well, the problem is this whole laundry list of hidden, everyday vulnerabilities that we've all just kind of accepted as normal. Transactions fail because of technical outages at a centralized bank, they fail because an account gets randomly flagged, or someone hits some arbitrary daily transfer limit, or surprise, transfer charges completely drain the funds. Our transactions rely 100% on a central authority, a middleman, that basically acts as a massive bottleneck. To fix these exact problems, cryptocurrency was born.
Section 1. Anatomy of a block. The decentralized dinner ledger.
Okay, let's replay that exact same dinner, but this time using Bitcoin. Let's assume Phil, Ted, and Sam each have 3 Bitcoins in their reserve, and Jack has 5. First up, Phil sends 2 Bitcoins to Jack. Instantly, a record is created. This is our block. But here is the really surprising part. This block doesn't just record the transfer. It actually holds the updated reserve balances for everyone. This single block permanently inscribes that Jack now has 7 Bitcoins and Phil has 1. And when Sam and Ted send their shares, brand new blocks are created, logging those exact same updates for everyone in the network.
And this right here perfectly illustrates the core architecture. These blocks aren't just floating out there randomly in cyberspace. Each block takes a direct reference from the previous one to verify the exact number of Bitcoins everyone owns. They physically link together. This unbroken, continuous chain of records is what we call a ledger.
But what happens next is even more interesting. You're probably wondering, well, what if someone tries to cheat the system? Let's say Phil, who only has 1 Bitcoin left after paying Jack, tries to pull a fast one and send 2 more Bitcoins to Jack. Can he actually trick the system?
The answer is a definitive absolutely not. The transaction will completely fail. Why? Because this is not some private bank database hidden behind closed doors. This is a public distributed ledger. The ledger is shared among all the friends. Every single user has an exact copy. So when Phil tries to spend money he literally doesn't have, everyone else's copy of the ledger clearly shows his balance is only 1 Bitcoin. The network immediately flags the transaction as invalid and tosses it out. This completely shatters that common myth that a hacker can easily just jump in and alter your digital funds. A hacker cannot alter the data in the blockchain because they'd have to alter it on every single user's copy simultaneously across the entire globe. It is strongly resistant to alteration.
Section 2. Cryptography. Securing the block.
So how do we prove who is who? Well, every single user in the network relies on 2 unique keys. First, you have a public key. Think of this kind of like your email address. It's an address everyone in the network knows so they can send you funds. Second, you have a private key. Now, this is a unique address that absolutely only you know, acting exactly like a highly secure, unbreakable password. When Phil sends his Bitcoins, he physically signs the transaction using his private key. That proves, without a doubt, the money came from him. The message is then transmitted using Jack's public key, and guess what? It can then only be decrypted by Jack's private key.
Now here's an incredible advanced insight for those of you wanting to look under the hood. All of these transaction details are locked up tight using complex mathematical hashing algorithms. But not all blockchains use the same digital armor. For example, Bitcoin relies on the SHA-256 algorithm. Meanwhile, Ethereum, which is another massive cryptocurrency, uses a totally different algorithm known as Ethash. Pretty cool, right?
Section 3. Mining and Validation. The network's defenders.
This brings us to the true defenders of the network, the miners. All around the world, transactions exactly like Phil and Jack's are taking place constantly. To validate these blocks and actually add them to the chain, miners have to solve an incredibly complex mathematical problem. This really demanding process is called proof of work. They are literally mathematically proving that their computers put in the required computational work to verify the transaction's legitimacy. And the whole process of adding that newly validated block to the chain, that is what we call mining.
Okay, but why on earth would anyone spend massive amounts of electricity and computing power to do this? Well, the answer is 12.5. The first miner who actually solves that mathematical problem and successfully adds the block to the chain is rewarded with 12.5 bitcoins. That is a massive financial incentive. It's exactly what keeps thousands of independent computers constantly working to secure the network, completely eliminating the need for a central bank. Once that block is added, Phil and Jack's wallets are officially permanently updated.
Section 4. Beyond crypto, real-world use.
There's a huge misconception out there that blockchain is only useful for digital money. So let's look at a real-world example featuring Walmart. Walmart had a huge problem. They had this massive, sprawling supply chain and a really high return rate for damaged goods, but zero way to track exactly where the damage was happening. Was it the farm? Was it the transport trucks? Who knows? So Walmart adopted blockchain technology. Just like logging a Bitcoin transaction, they used blocks to permanently inscribe the quality of goods at every single step of the journey, from the farm origin all the way to final delivery. So now if a customer flags a damaged product, Walmart just checks the blockchain to instantly and correctly identify exactly where the failure occurred. They identify the problem and they fix it.
So strip away all the hype, the crazy crypto prices, and the technical jargon. What exactly is a blockchain block? At its core, it is simply a permanent, unalterable record of truth. It's a chain of records, fiercely resistant to alteration, protected by heavy cryptography, and validated by a decentralized network, so no single bad actor can ever change the data.
We've seen how it bypassed the clunky, totally failure-prone traditional banking system for four friends trying to pay for dinner. We've seen how it saved a multi-billion-dollar retail giant from a supply chain disaster. If this technology guarantees a permanent, completely unhackable record of truth without ever needing a middleman, what other broken systems in our world could a blockchain block fix? Voting? Real estate? Our medical records? The possibilities are literally endless, and honestly, we are just getting started. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll see you next time.